here. This is the title of my talk, the Gribov problem in non-commutative QED. This is based on a work which I'm doing in collaboration with Fabrizio Canfora in Chile, Max Kurkov in Brazil, and Luigi Rosa in Napoli, in my department. Okay, so what I will do first is to review what is the Gribov problem in usual, in commutative gauge theory, because I imagine that not everybody is familiar with it. So I apologize with those who know what the problem is. I will first describe the problem the way physicists see it, and then I will try to give a geometric picture of the problem. Then I will shortly review what I mean by non-commutative QED for a special kind of non-commutativity, which is the usual constant one that we all know. And finally, I will go to the problem in the framework of this non-commutative QED. And I will give some comments at the end. Okay, so what is the Gribov problem in gauge theory? This is connected to the fact that gauge theories are constrained theories, so we have to choose a gauge when we want to quantize them. So what are the ingredients that I will use? What is the notation? This A, calligraphic A, is the space of gauge connections, all of them. Then I have my gauge group, which is an infinite dimensional group, and it is the group of maps from my space-time, which is Euclidean, to the Lie group G, which will be UN or SUN. And with this condition here, so essentially I am trading this R4 for S4 with this condition that I am imposing. And this B, this calligraphic B, is the space of physical gauge connections, namely those which are gauge equivalent to one each other. Equivalence classes of gauge connections. So this is the action. Without this, oh, I'm sorry. Without this red indices and trace here, this is just the Maxwell action. Otherwise, I have to put my connection is valued in a non-abelian Lie group, so I also have Lie algebra indices here, and they come from tracing over the Lie algebra. This is the curvature F. In the case of U1 theory, of Maxwell theory, I only have this contribution here because the gauge, the Lie group is U1. Otherwise, I also have this part here.
In non-abelian also, it's not only quadratic, actually. Or M depends on
M will be a generalized M, which contains everything. So here I will, for now, I stick to M for the abelian gauge theory. So M is this object here. And what is a problem? The problem is that this M is not invertible because of gauge invariance. Namely, I have 0 modes. For example, this object here is at 0 mode. When I plug it into M, I get 0. So being not invertible, I can't do what is usually done for scalar field theory, where I perform the Gaussian integral here. And in order to perform it, I would need the inverse of this M, which I actually don't have. So how do we proceed? We have to fix the gauge. And this is done by introducing into the action a delta function. This f of a minus h is a gauge fixing. And I have to replace the integration measure here, which is over the space of all connection, with an integration measure which is instead on the space of equivalence classes of connections. So the problem that we have is to define this d mu a over g. So what is the problem here from a geometric point of view? The problem is that fixing a gauge this way amounts to choose a surface in the space of connections. Namely, it amounts to choose a section for this fiber bundle here, where I say again, A is the space of all connection, B is the space of equivalent classes of connections. G is what I call the map group from R4, let's say, to the Lie group G. So in general, we don't have this global section. But for now, let me ignore these global issues and just proceed the way physicists do. So locally, we will write the total space A as a product. Then the measure will be just the product of measures. Then if I choose, if I perform an expansion of my gauge transformation around the identity, this measure over the gauge group, I can write it this way. And then I want to perform this change of variable here. In order to make it, I have to insert the Jacobian of the transformation. This operator here, delta, is what is called the Fadeev-Popov operator. So I insert it in my measures here, and I get this expression. I recall that we want to determine d mu b, d mu over the quotient space. So here I really have a change of variables. So I have replaced my d alpha with this df of A. A is an index that shouldn't be here because we are, well, if we have a non-abelian gauge theory, I also have this index A. This is a Lie algebra index. So what I do now, I integrate over this dfa using the delta function that I had for gauge fixing, and I have obtained my d mu b here, because the integral of this times the delta function will disappear. So I have obtained my d mu b in terms of the measure over A times the Faddeev-Popov determinant times this delta function. So this is the way I will replace my integration measure into the functional integral with the physical integration measure, which is this object here. Of course, I ignored all global issues because I am assuming that this is true overall, but this is not indeed, as we have topological obstructions. So let's see what are the topological obstructions in the usual commutative gauge theory. So the space A of all connections is a topologically trivial space because it is an affine space, as I can see from here. I can, for given two gauge connections, I can connect them with a straight line. This is still a gauge connection, as I can check from here. I simply do the transformation here. I have this minus tau, and tau will combine in such a way that I get only this term. So this is a gauge, this is an affine space. Then it is topologically trivial. So the only way it can be globally the product of B times the gauge group is that also B and the gauge group are topologically trivial, which is easy to see is only the case in the case of QED. So what is the situation in general? G is this group here. As I said, this is essentially maps from S4 to G. Then when I compute the first homotopy group of G, this will be essentially maps from S5 to G. Then we have this relation here between the first group of homotopy of my gauge group and the fifth homotopy group of the Lie of the finite dimensional Lie group, which can be U1, U2, and so on. And I have this situation here. When G is UN with n greater than 3, pi 5 is known, and it is Z, so non-trivial. It is Z2 when I have U2, so it is non-trivial. It is only trivial when n equal 1, namely U1. So only for QED. What happens to B, to the base space? Base space is A over G. There is this nice relation between the homotopy groups of A over G and G. So again, I have that B is only trivial when G is equal to U1. So this is why we have copies. We have copies in general for non-abelian gauge theories because we can't choose global sections. The reason being that the fiber bundle that I have is non-trivial unless we are in QED. Okay, so this is what I said. Non-abelian gauge theories do not admit global sections. Locally, let's say physicists see this as looking at the Faddeev-Popov operator and noticing that it has non-trivial zero modes. Namely, the determinant of the Jacobian changes its sign when the surface of gauge fixing meets the gauge orbits more than once. So what is a solution that has been proposed some time ago? The solution is essentially due to Dell'Antonio and Zwanziger in the 90s, I think. I quote a paper in the end, and we will check the exact date. And they show that what you can do is to restrict the functional integral to some region. This region is characterized in this way. Well, the characterization comes from the second point, actually. It is the region characterized by the Faddeev-Popov determinant changing sign at the horizon, at the boundary of this region. So they stay into the region where this object does not change sign. Then they have shown that the region is bounded in every direction. And also that when you are in this region, you are not missing any non-equivalent gauge connection. Namely, all gauge connections pass inside this grid of region one and only one time. And then they implement the constraint of integrating only over this region where the Faddeev-Popov doesn't change sign with a delta function, which amounts in a new contribution in the action, which modifies the propagator in the infrared, and the propagator is modified in this way. So for small p, so this is in Fourier transform. So p is the momentum. For small p, you have a modification of the usual object. Okay, so this is the situation for the commutative case. Commutative flat case. Yes.
I really quite understand the problem. I mean, you have a bundle that's non-trivial, so it's a global section. But you can just take local sections and integrate on different patches and add up the results. So why can't you just do that?
Well, you are essentially taking a local section because you are restricting to a region where your Faddeev-Popov object doesn't change sign. But they show that it is sufficient.
But why not take several sections so you cover the whole space? Just add up the results.
I don't know. Probably.
Choose different patches, you get different results.
Yeah, you add them all up and you should get...
No, but depends on your choices. No, yes, it does. It's not trivial cohomology class.
You made a mistake, right?
No, but class is not trivial. No trivial cohomology class. So
But if that doesn't work, the whole thing isn't defined.
But you're not
Well, it's
integrating
not.
over the quotient, right? You're doing gauge fixing.
Yeah.
So you're actually also using the fact that you have an affine space plus gauge
Mm-hmm.
fixing, which is then restricting to this Guido region. But you're not doing the integral on the quotient because it's just
But you're trying to
Yeah.
define the integral and quotient.
No. You are rephrasing your integral on the quotient in terms of an integral over a, plus modifications in your action. So the action gets modified, but you are still integrating over a. In the end, this is actually what you do. I showed you that a is some parameter here. No. It does not come from the Lie group. is some scale, let's say.
Okay, so what does it mean?
Sorry, let me show you the measure. Here, you see, we rewrote the integration over the quotient space as an integration over A. These terms here, you can rewrite in such a way to modify the action. They will just contribute to the action. This one will be in terms of the ghosts. This will be just the kinetic action of the ghost. This will give. And this other one, actually, you will also rewrite in such a way that it is some additional contribution to the action. So you are doing your integral over A. That's what you gain. Modifying the action without modifying the space of connections, let's say. So we were here, exactly. So okay, this is for the commutative case. You can imagine at this point that we expect copies in non-commutative QED because even if U1 is a billion, the gauge group will be non-commutative due to the non-commutativity of the star product. So we do expect copies, but let's see how it works. So here I shortly review the notation. So this is my Moyal algebra. It is the intersection of the left and right multiplier algebra defined in this way. S are Schwarzian functions. This is the dual algebra of Schwarzian functions. The product is well defined for Schwarz functions, and it is extended to the dual algebra S prime by duality. This is the matrix theta. We are in 2D dimensions, and in principle, this theta 1, theta 2, and so on can be all different. This algebra, it's a big algebra actually because it contains Schwarz functions, it contains polynomials, constants, and so on. What is the differential calculus that I am using? It is this derivation-based differential calculus, which was introduced in the gauge theory context by Dubois, Violette, Thierry Masson, who is here, and Jean-Christophe Wallet. And these are the derivations. They are inner. They are the algebra, of course. Well, they are not a left module in the sense that when I left star multiplied by a function, I don't have a derivation anymore. I defined the whole differential calculus algebraically. I defined the D and the contraction. Forms are defined by duality with respect to derivations. So I construct omega 0, which are my functions, or omega 1, which are my one forms, and so on. So it can be defined, let's say, constructively. What happens to vector bundles of matter fields? Vector bundles of matter fields are replaced by right modules over the algebra. We have an Hermitian structure. Mi are in the module. F are in the algebra are theta. And I define a connection. This is the connection. It is defined in terms of this covariant derivative here. M is, as I said, in the module H. F are functions. The connection has to preserve the Hermitian structure, and it is completely defined by its action on a basis in H. So we want to concentrate on QED, which means that we want to generalize the U1 connection to the non-commutative case. So the module will have just one generator because I have U1 here. Then it will be of this form here. This is the module part, and this is the algebra of functions. And then the gauge connection is defined by its action on the single generator of my module. It is this object here. And I can, by using this relation here, I obtain its action on this module. So A mu is the gauge, A is the gauge connection one form. What are gauge transformations? They are automorphisms of the module, preserving the Hermitian structure. Namely, they are the unitaries of my algebra, and this can be seen in this way. I have to impose that they preserve the Hermitian structure, so I write it explicitly, and I get this relation here, which is telling me that they are the unitaries. So we pose gamma of 1 here. 1 is the generator of my module, equal to u. U of x, this is a function over R to n. And here I have the properties of the gauge connection. So this is how it transforms under gauge transformation. This is how the connection one form transforms under gauge transformation. So the usual one with the commutative product replaced by the star. This is a curvature, and it is covariant as we expect. So this is the setting. With these objects, we can write an action. This action can be seen to be gauge invariant and Poincaré invariant once we have decided what we mean by Poincaré invariance, but I don't want to enter into this. And, well, sorry. We know that it gives problems because there are new divergences with respect to the commutative case, which are coming from the mixing of the ultraviolet and the infrared region. But I will not address this problem here. I want to show the appearance of copies. Probably in the end, I will just make a comment between a possible relation between the mixing and the appearance of copies, which is a bit controversial, but, well, I will tell you. Okay, so for the rest of the talk, I will use this asymptotic form of the star product that I showed you in integral form in the beginning. This is a transformation of the gauge connection under U1 here. U is a star exponential, namely it is a series. And I can write the infinitesimal gauge transformation, which now has here this d mu alpha. What is this d mu alpha? It is this object defined here. So with respect to the commutative U1 case, I have gained this contribution here, which is responsible for the appearance of a non-trivial equation for copies in non-commutative U1, because now formally this is similar to the gauge transformation for non-abelian commutative theories. So what do? We choose a gauge, for example, the Landau gauge. Well, actually, the Gribov problem is always addressed in the Landau gauge, although there are some papers where it is shown that the problem persists, for example, in the Coulomb gauge or in other gauges. There is a paper by Olaf Lechtenfeld where he shows that it is not true that the problem is gauge dependent. Anyways, the gauge, the Landau gauge is easy, and so we stay with this choice. Then I impose that my gauge transformed field A mu satisfies the gauge condition. And I find this equation here, which is actually the equation for the existence of copies. Namely, it is the equation that is telling me that the gauge fixing is actually not sufficient to fix the gauge. Because if I have non-trivial solutions to this equation here, it means that I have a whole family of gauge equivalent fields which satisfy the gauge fixing condition. So I have not fixed actually the gauge. The difference with the commutative U1 case is that in the commutative U1 case here, I will just have d mu alpha without a covariant, the Lambertian, let's say, of alpha equals 0 in the Euclidean, which only has trivial solutions. If we choose reasonable boundary conditions, while here this can have non-trivial solutions, precisely because d mu alpha is now of this form. So what is the equation that I get when I go in Fourier transform? I get this equation here. This k is a variable in Fourier transform, where the operator q is given by this expression. So I have an integral equation for the copies. So I have recast the problem of looking at Gribov copies into the problem of solving this equation, which is a homogeneous freedom equation of second kind here. Okay, so at this point, what we have done? We have studied some general properties of this equation here. For example, we have shown that it can be put into a form which makes it manifest that the operator is symmetric. But what I want to tell you is not about the general properties of the equation, but actually show that I have solutions and I have a whole family of solutions. I really have an infinite number of solutions, namely of copies, if I choose some potential A. So the strategy has been, let's choose some simple potentials A and see if we can solve the equation and see if we can actually exhibit copies. Because, let me say again, the point was to show that not only there can be grib of copies, because the theory is similar to a non-abelian theory, but there are indeed copies. So what was the first choice? The first choice was a simple potential of this form, linear in X. Why did we choose this? Because when we go to Fourier transform, this will give you a delta function, delta prime. And then the integral equation that we had will become a differential equation because I can integrate my delta function, and then it is simple, let's say, to solve. So with this solution here, I will tell you why I call it the gauge invariant connection in a while. This can be seen to verify the Landau gauge. It is very simple because this object here is antisymmetric. So, and in Fourier transform, as I said, is the derivative of a delta function. What we find is that for this gauge potential, the equation of copies is actually identically satisfied. It is satisfied for any choice of alpha. So we were actually very, very, very excited when we found it, because we said, okay, we have an infinite family of solutions. The problem is that this connection here is actually gauge invariant. It is known, yeah? It is known to people who have worked in non-commutative QED in this approach, that this connection is not only covariant, it is invariant. It is a fixed point of the gauge group. So when I apply the gauge group, I actually don't generate new fields, so I don't have copies. I don't move my connection by applying the gauge. Yeah.
From this very last comment
Yeah.
you made,
Yes.
what you said is can be as a parallel for non-abelian gauge theories. So the previous slide was exactly the same for non-abelian gauge theories, or I'm missing something?
Yes, it is exactly the same in non-abelian gauge theory. You just have, you not only have non-commutativity, you also have non-abelianity. But in that case, you do expect copies because you have them in the commutative case. So this is the simplest non-commutative example, and the appearance of copies here is genuinely non-commutative. It is not an effect of the theory being non-abelian.
So you use non-abelian?
Non-abelian, I mean the gauge group.
Non-commutative when there is
Yes.
a star product. Okay.
Non-abelian, I mean the Lie group in the commutative case is non-abelian. Okay.
Can you always solve the gauge condition? So is there always a gauge transformation into a potential that satisfies that?
But why do you want to solve it? I mean, I want to fix.
Yeah. So do you intersect every orbit by fixing it? That's my question.
Well, here what I'm doing, No, actually, I want to show that I can't. I mean, that since there are copies, I can't gauge fix, because I will have a whole family which obey the same gauge fixing condition. So in this case, as I said, I have a whole family, but they all coincide because the gauge connection is invariant. So no new copies. So what is the next to the simplest situation that we chose? We keep going with our polynomials in X because we like delta functions, because in that case it will be easier to solve my Friedholm equation. Yeah?
How does f behave with such polynomials? Does it decrease
What is F?
the field strength? Does
The
it
field
decrease
strength. So what you have to do then it is to smear your potential.
decrease it?
No.
So it's no
It is not really physical, let's say. But you can say that you can approximate this object with some physical potential. Probably. Anyway, here the point is just to show that you have these copies. I agree with you, and we actually discussed about having more physical choices. So let me now, for simplicity, to consider the two-dimensional case. You can check again that this choice of the potential satisfies the Landau gauge because of anti-symmetry of my theta. This is what I get in Fourier transform. So I have derivatives of the delta function. So I plug it into my integral equation. I integrate and I get a differential equation, which is this one. This comes from the integral Friedholm equation when I replace for this a mu. And now I can think of solving it because it is afterwards a differential equation. It was not so easy actually, and without Max Kurkov, I think we wouldn't have solved it. Anyways, we solve it in spherical, in polar coordinates in the plane because, well, we can do because epsilon in 2 dimensions is an invariant tensor. It's a long story, but I just flash here the solution. This L here has generalized Laguerre polynomials, so a whole family of solutions. So, and we did exactly the same for the 4-dimensional case. We also have a whole family of solutions in that case. Okay, so I'm almost done. So what we have done, we have studied noncommutative QED with Moyal noncommutativity, and we have found an equation for copies. We have studied some of the properties of the integral kernel for our Friedholm equation. And we have explicitly, we have chosen some simple potentials, and we have explicitly shown that then the equation can be recast in a differential equation that we are able to solve, and we found copies, sorry, too fast. Okay, what would be the outlook? The outlook is a list of questions that need to be answered. So first, can we apply the Gribov-Zwanziger-Dell'Antonio restriction to this case? Namely, can we cure this problem of copies with some similar technique, looking for a region where there are no zero modes, and such region should be enough to capture all non-equivalent gauge connections. We don't know. What would be, in that case, the modified propagator? And then the question, is there any relation with the ultraviolet infrared mixing? Why did we ask this question? Because the modified propagator that I showed you in the commutative case is exactly the propagator which has been used by people like Blanchke, Sveda, and so on, to cure the mixing for gauge theories. So, is it a coincidence, or there is a relation between the two phenomena? We don't know. And to answer this question, well, this is the global question that I wanted to address also, namely, can we give a nice picture of this problem in the same way as we did for the commutative case, where we have a nice geometric picture to understand why do we have copies, namely the appearance of non-global sections and so on? I don't know. But let me go back to this point here. So, we thought that in order to answer the question, is there a relation between the mixing and the appearance of copies, since the mixing is a problem already in scalar non-commutative theory, where there is no gauge, probably we should look at a scalar theory, remove the gauge complexity, let's say, and look for some symmetry of the scalar action. So for this transformation here, what happens is that the potential doesn't change, because the potential is a polynomial in the fields. It is only the kinetic part of the action which will change. So our idea was to look at the equation that we would get for this U here, interpret it as an equation for the copies, and see whether or not this gives a correction to the propagator. In this, we were inspired by the fact that there exists a scalar non-commutative model, field theory, which is due to these people, where the propagator is modified to cure the mixing exactly in the form of a Gribov-Zwanziger propagator. There is in the kinetic action, besides the Laplacian, the D'Alembertian, 1 over the Laplacian, which gives that P 1 over P squared that I showed you in the propagator of Gribov and Zwanziger. So the idea would be to investigate already in the scalar case if the problem of the mixing and the appearance of some Gribov-like copies are connected phenomena or not. And this is a paper where essentially this non-commutative QED is discussed. This is a recent paper of Daniel Blanchke, where he reviews the approach to the ultraviolet infrared mixing in non-commutative gauge theories using a modification of the propagator. And finally, this is the paper that I was telling you about, this scalar model, which is modified by a 1 over the Laplacian in the kinetic part in order to get rid of the ultraviolet infrared mixing. And with this, I'm finished. Questions? Reimer?
So I have a comment on your modified propagators. So this is an extremely dangerous business because you risk to violate the spectral condition that the joint spectrum of the generators of translation is in the form of light group. So you generate poles in somewhere else. And then you are no longer allowed to, well, to transform to the Euclidean world. Because you need precisely the spectral condition to have this Euclidean formulation. So there is no partition function.
This is Euclidean.
This is Euclidean.
Yeah, but
You mean there wouldn't be the Lorentzian analog? Yeah, eventually. Walter?
So this one potential that you had, which you said was kind of gauge invariant.
Yeah. Phi star, phi star, phi star, phi.
So how do you deal with it? Because it still appears in your integral.
Well, you have u phi u minus 1, u phi u minus 1. So you only have a global u. I mean, it really appears in the kinetic action because there I have derivatives of my field. So I will have derivatives of this u.
Yeah. So it would give a contribution, which is even a continuous family.
Actually, the potential doesn't give a contribution. It can be shown that you can get rid completely of that factor. It is only the kinetic part which contributes.
And then, so
And we have an equation, but we just have an equation. We didn't solve it. It's preliminary. Other questions? I am doing the chairman, sorry.
There are no other questions.